Welcome to part 3, probability measures and expectations. We're going to see the axiomatic probability model now. Probabilities, if we are modeling random phenomena, should be associated with events in order to reflect what we believe is the likelihood of those events happening. So it has to be a logically consistent model. And this is what the axiomatic probability model provides. A probability measure on a measurable space, omega f, is the set function that satisfies the following. First of all, this function has to assign a 0 probability to the empty set, meaning that the probability of nothing happening is 0. On the other hand, every event that is in our dictionary or our sigma algebra should have a non-negative likelihood of happening. Then for any countable collection of disjoint sets, they have to be disjoint, the probability of the union of the events, so the union is interpreted as, the event, this and that happening. So the probability of that union is the sum of the individual probabilities. And the last condition is that the probability of something happening has to be 1. So the probability of the whole set is equal to 1. I should make a little remarks on 2 of these conditions. We ask for the probability to be equal to 1, the probability of capital omega, because that reflects the fact that something has to happen. But there are some models that are important, particularly in simulation and rare events, where we might want to have the probability of the whole of omega being different to 1. When this is not true, when the probability of capital omega is not necessarily equal to 1, then instead of having a probability measure, then we're going to be working with a measure. So it is a different measure, not necessarily probability, but it will also be a measure. And the other remark I'd like to make is that when we don't have the condition of the probability of events being non-negative, so if we do not have this condition, if this is taken out, then what we basically have is a signed measure, what is called a signed measure, where the measure of some sets, some subsets, could actually be negative. This is going to be relevant for our stochastic optimization course when we see gradient estimation. But for the moment, we are going to work with the usual definition for probability, which is this, which has these 3 properties. So if we have a measurable space, omega f, and we add to this set a probability measure, now this space, which has 3 components, is called a probability space. And it already contains that probability measure. As an example, we're going to see a very simple example, of course, example from textbooks. If we have 1 die, then the possible outcomes are from 1 to 6. I'm basically just calling the omega, I'm calling it 1, 2, 3, 4, 5, 6. So those are the possible outcomes. And if we assume that the die is fair, then we're going to assume that the probability of each of the outcomes is equal to 1/6. So this is the regular assumption that we are going to see in many examples. Now, I do want to remark something about notation. The shortcut for writing this is usually seen this way. The probability that the die comes out in 3 is equal to 1/6. In reality, we should be writing the probability of the event that the die comes out in a 3 is equal to 1/6. Now, in mathematics and generally in all science, we try to be economical and economical in our notation as well. So for the intelligent reader like you that is going to be able to interpret things, we're often going to take out the brackets. They're left out. But as long as you understand that the probability is actually defined on a sigma algebra, so it's a function that takes sets, not outcomes, is a function of the events, then that will be fine to let go of that notation. And just as a little remark, if the probability was defined as a function of in omega and not on the sigma field, then it would be a random variable, not a probability measure. We denote by curly B of R the Borel sets in R, which is basically the sigma algebra generated by the subintervals in R. If we have a random variable defined on a measurable space omega F, because X is a mapping from omega into the reals, then this will induce a probability measure on the image spaces, which are the reals and their Borel sets. So the definition of a probability distribution of a random variable is a function that takes values from the reals into the interval 0, 1. And it is given by the probability that the random variable be less or equal to X. So again, letting go of the curly brackets, although we are meaning a probability back in a subset of the space omega, you're gonna see this written down in a shorthand notation as just the probability that capital X is less or equal than X. But the meaning of that is going back to the set omega. So the actual meaning is the one that is in the rectangle, in the red, highlighted in the rectangle. Let us take a look at a visualization of this. And so I'm going to share my iPad. The iPad was not connected correctly. I'm sorry about the dings. So we have a omega space here, and we have a mapping that goes, X is a mapping that goes into values of, the values of X go into the real line. Now, if we take a look at the definition of the probability distribution, then we take a subinterval. So we might take a subinterval from A to B. Actually, usually we take an open interval here. So we take an open interval from A to B. And we are trying to assign a likelihood to this subinterval, that X lies in this subinterval. So what we do is that we take the pre-image of that interval, and of course the pre-image is a subset of omega. So the probability of the set omega such that X of omega is in the interval A, B will be basically the probability of that event E. Now, this probability is defined as a function of our sigma algebra into 0, 1. So for this scheme to work, we need to know that the event E is correctly defined as being an element of the sigma algebra. But why is this always true? that the pre-images of X, of the random variable X, are actually sets contained in the event sigma algebra? Well, the answer is, by definition, X is a random variable on the space omega and the sigma field. So by definition, X is measurable with respect to that sigma algebra. And there it is. That is the answer, that indeed this is well defined. If X is a random variable that is defined on the measurable space omega f, then it is true that for any subinterval, the pre-images of the X random variable are all going to be contained. So the answer to that is that yes, these events are well defined inside F, and thus we can assign them a probability, because this function probability is only just defined from F to 0, 1. So everything is consistent in the model. Everything makes sense. I would like to make a remark now. This is a personal view of mine, and it might not be shared by everybody, but we have basically, this is so the set of omega, of possible, the capital omega, the possible outcomes, and we have a mapping here, and the mapping here is a random variable. A random variable. And this maps into the reals. So this, on the right-hand side, what we have is the study of certain numbers and how these numbers behave collectively. To the left, what we have is set theory, because omega is a set and the sigma field F contains subsets. Now, in my view, this to the left is the world of probability, or, well, probability theory. And to the right is the world of statistics. Of course, now we know, nowadays we know that probability and statistics really belong to the same area of research. But historically, they started very, very differently. I'm not going to go into the history of statistics or probability, but basically to point out that the word statistics comes circa 1400s in the Republic of Venice. Where the data about the population was used for purposes that included commerce, taxes, and military recruitment. So it was very important for them to keep statistics, to keep the numbers. And actually, one of the ways that statistics was defined early in the 15th century was the systematic collection of, it was socioeconomic data for the state. And that's the word statistics. It was conceived to be, statisticians were privy of information that was exclusive for the state. And it was very similar to what national security agencies would do now. So that is the origin of statistics. It became very well developed in the 1600s. Of course, during the plague in Europe, there were all the statistics about all the deaths that were happening during the plague. And this comes back to the 1300s, then in the 1400s, then 1500s, and in 1610 towards 1640, it was used in the court of England all these numbers in order to make predictions or to make important decisions. And around the 1600s, actually 1660, we find John Grant, who basically created what the basis for what is today modern statistics. And it was the tables of mortality that he was analyzing. So basically statistics models. So statistics basically is focusing on modeling. This creates models to summarize data, particularly large amounts of data. So that's what it started with. So what about probability? Probability develops much later. And the birth of probability, the way that we know it today, is perhaps, arguably, the letters written in 1654 between Blaise Pascal, and Pierre de Fermat. And the history of it is, well, I believe very different from the history of statistics. Pascal was a young, very clever mathematician and scientist at the time. And he really liked gambling. In that time, in the 17th century, in France particularly, gambling was a tremendous industry. A lot of people were allowed to go to gambling houses, and people made a lot of money, and they took this very, very seriously. So it is said, it is documented that Pascal really liked it. And he had a friend, a gambling friend, who was called Antoine Chevalier de Méry. And this person was constantly on these gambling houses, making up new games, and he was making money out of that. And so he asked Pascal if Pascal, being so clever, could perhaps help him understand the odds. So they were talking about odds, they were talking about games, and they were talking about predictions in order to be able to take advantage of that, a financial advantage of that. So these letters between Pascal and Fermat are documented very nicely in a book. And they actually illustrate how they were thinking about the phenomenon. It wasn't described with the mathematics that they knew just yet. So they basically create a new model of mathematics to deal with this. Very, very soon after Pascal and Fermat talked about this, Pascal actually died very young. He was much younger than Fermat, but he was very sick. And very soon after, the Bernoulli family took on their ideas, and they developed that much later. Of course, the Bernoulli family had a lot of mathematicians and great thinkers in their family. They were only among the nephews and cousins, there were like 8 really brilliant mathematicians. But importantly not, Jacob, the head of the family, was a Swiss banker. And he realized immediately that the ideas that started describing games of chance could very well be applied into banking and finances. So that gave a lot of development of probability. Bernoulli was the first one who talks about confidence intervals and things like that. And of course, in the Bernoulli family, not only Euler was he married one of the Bernoulli nieces, but also we have other very important mathematicians that were associated with the Bernoullis. What happened later was, well, we had to wait until the 1900s. Basically, late 1800s and early 1900s, we have the Russian scholars notably Kolmogorov is the one that postulates the axiomatic probability model as we know it today. We also have names like Markov, which are going to become really important in our simulation course and also in the other course that we're going to be teaching. And so we usually associate the development of probability with the schools, mathematical schools in France and Russia, whereas the statistical schools are associated mostly with early development with England. Of course, later on, we will have also the French, and we will have Gauss, and we will have all of those people that are working already with a view to mix or to join the power of probability and the power of statistics. So what they were trying to do in there was model to predict likely outcomes. And estimate risk. So again, as today we know this is part of the same discipline, probability and statistics, but the outlook, particularly historically, of each of the disciplines was a bit different. And we still see today a little bit of that division on the kind of work that people do, whether it's probability or statistics. The exercise for you is the following. Let's consider again a fair die that has 6 possible outcomes, and each of one has the same probability. And I'm giving you a particular random variable. It's a function that is defined on omega, and it is a random variable with respect to the largest sigma algebra, which is going to be the power set of capital omega. And I'm asking you to evaluate what is the distribution of x. Again, as usual, you can pause, take your time, and try to do that so that you actually put your knowledge into work, or you can do it later. I'm going to introduce the expectations first for countable space. When we have a random variable on the probability space omega, f, and p, and it has values in a countable space, then we can define a partition of omega that basically maps back, tells us which are the parts in omega, which are the subsets of omega, where x has a constant value. So for each of the possible values, I is an integer. So for the possible values of x, we map back all the parts of omega. So because there is a countable number of possible values of x, there will be a countable number of subsets, and they define a partition of omega. So we take the sigma algebra generated by x as being, as we have seen in other parts, the power set of this partition. So now we define the expectation of the random variable x as the weighted sum or weighted average of the atomic values xi in x. And this is the familiar formula that you should have seen already in your previous probability subjects. We can generalize this, of course, with when x is a continuous random variable. It has a distribution f and a probability density, which is the derivative of f, of capital F, and the expectation is well defined and is defined again as the integral. So these are the definitions that you're already used to. I'm not going to go very much into this, except for next part where we're going to be calculating expectations by conditioning. Next time, we're going to see conditioning. So until next time.